The next demonstration scenario addresses an application of active antenna systems, a technology which in a given use case is exploited to vertically sectorize LTE macro cells. Vertical sectorization effectively increases the frequency reuse density by splitting a macro cell into an inner cell with a footprint close to the base station site and an outer cell serving more remote users. In the demonstration scenario, the frequency resources of the macro cell are reused in both the inner and the outer cell, while the original macro cell's transmit power is split between the two cells. When deployed effectively, vertical sectorization enhances network capacity and hence service performance. As we did previously, we first consider a baseline scenario where the SON function is switched off. We zoom into a relevant urban area of about 2 by 2.5 kilometers in the center of Hanover on the network panel by clicking the AAS button. The considered area features 30 LTE macro cells with a 20 MHz bandwidth assignment in the 1800 MHz band. As said, in the baseline scenario, the SON function is switched off and all macro cells are vertically sectorized with a 50-50 power split between the inner and outer cells. This permanent activation of the vertical sectorization feature, and hence the presence of the inner cells, is readily visible if we consider the best server areas on the network panel. Clearly, each site features 3 inner and 3 outer cells due to the combination of the conventional horizontal and the newly applied vertical sectorization approach. By right-clicking on one of the inner cells on the network panel, we again open the cell view panel for the selected cell. Even though at present the vertical sectorization SON function is deactivated, we can still display the settings of the control parameters in a control parameters chart, depicting either the cell's assigned transmit power or its activity status. Noting the fixed and known relation between the selected inner cell and its associated outer cell, the KPI chart allows also to show us the ratio of the outer and inner cell loads, or a throughput KPI for the inner cell, the associated outer cell, or for the aggregate of the two cells. The KPI panel shows 4 different charts with distinct performance metrics. Covering all users and cells in the shown area of Hanover, the top 2 charts show different user throughput and cell load percentile curves. The third chart shows the number of activations and deactivations of the vertical sectorization feature as measured over a sliding window of 5 seconds, which is equal to 0 in this baseline scenario as expected, since the feature is constantly active. The final chart shows the number of handovers, also measured over a sliding window of 5 seconds, which is also equal to 0 in the baseline scenario. As we will see in the scenario with dynamic cell-based activation and deactivation of the vertical sectorization feature, call handovers may in fact occur, even in the considered scenario with purely static users. This is due to the operational fact that upon vertical sectorization, the outer cell will inherit the physical cell ID of the original macro cell, while a new physical cell ID is assigned to the inner cell. As a consequence, ongoing calls that upon sectorization are best served by the newly generated inner cell are indeed handed over to the inner cell. Let us now go back to the operator panel, switch on the SON layer and the vertical sectorization SON function, deploy this change, and then shift to the next day via the time control panel in order to activate the SON function. The implemented vertical sectorization SON function is in charge of activating the inner cell upon an observed traffic load close to the site, dynamically configuring the split of the transmit power between the inner and outer cells largely in line with the relative traffic loads, and deactivating the inner cell again once it is deemed no longer needed. It is noted that, on top of the 4-degree mechanical antenna downtilt that is common to all cells, the electrical downtilt of the inner cells is currently fixed at 8 degrees throughout the area. In a further enhancement of the SON function, this will also be dynamically optimized. We can observe on the network panel from both the sector markers and the visualization of the best server areas how the inner cells indeed dynamically appear and disappear throughout the demonstration area. On the KPI panel we see that, as expected, the chart showing the window average number of activations and deactivations of the vertical sectorization feature now indeed shows positive values, with about 22 such changes occurring in reported 5-second intervals. Given the fact that we have 30 cells in the demonstration area, this implies that on average and on a per cell level, the vertical sectorization feature is then switched on and off about 8 to 9 times per minute. Also, the final chart, showing the window average number of handovers, now shows positive values due to handovers from the outer to the inner cell upon sectorization. The numbers indicate that, again on average and on a per cell level, about 10 calls undergo a handover per minute. Even if it is hard to see with the naked eye, the top chart shows that the 10th user throughput percentile, when aggregated over the entire demonstration area, shows a performance improvement of about 10 to 15%, indicating the benefits of self-optimized vertical sectorization for cell edge users. The gains observed by the application of self-optimized vertical sectorization are however noted to be most significant for heavily loaded cells due to the capacity upgrade that it offers, and are more clearly visible when examining performance on a per cell basis. When aggregated over the entire network, performance gains tend to be lower due to the existence of more lightly loaded cells that do not experience any significant performance benefits. In more extensive simulations of the greater Hanover area, cell-specific gains of up to 80% have been observed when comparing the 10th user throughput percentile measured over the aggregate of the inner and outer cells for the scenarios with SON-based versus a static deployment of vertical sectorization. Let us now again use the cell view panel to concentrate on the same cell as we looked at before. Now that the SON function is active, we can find the associated configuration parameters in a cell attributes frame. One of these configuration parameters is the activation/deactivation threshold, which dictates whether the determined ratio of the outer versus inner cell loads is deemed low or high enough for the inner cell to be activated or deactivated respectively. The other configuration parameter is the so-called power split factor, which sets the significance of affected calls in neighboring cells in determining the transmit power split between the outer and inner cell. If we set the control parameters chart to show the activity status of the considered inner cell and set the KPI chart to show the load ratio metric, then we can indeed observe that whenever the load ratio falls below the activation/deactivation threshold, and whenever it falls in the green value range, then the inner cell is activated, while it is deactivated when the load ratio falls in the red value range. Hence, when the measured cell load in the inner cell is deemed too low for keeping the inner cell alive. A second aspect we can observe from the control parameter chart is that the inner cell transmit power fraction, positive only at times during which the inner cell is active of course, is varying over time, as it is adapted to match the varying traffic distribution over the inner, the outer and the neighbor cells. Lastly, to see the bottom line performance effect of self-optimized vertical sectorization, if we look at the 10th user throughput percentile for the aggregate of the inner and outer cell, the keen observer notices a clear performance gain from applying SON-based vertical sectorization to this particular cell in Hanover. As mentioned before, significantly higher throughput gains, even up to 80% for specific cells, have been observed in the more extensive simulation studies done for the greater Hanover area. Such performance enhancements exemplify the significance of the gains from self-optimized vertical sectorization, particularly in heavily loaded cells. As we saw before, gains found in aggregation over a larger area covering a mix of lightly and heavily loaded cells are often smaller. Clearly, areas of high traffic demand is where capacity expansions are most needed, and a self-optimized deployment of vertical sectorization is shown to be a promising feature to deliver this.